In this lesson, we're going to start off deriving the law of cosines. And we're going to start with a similar process as we did with the law of sines, where I have a triangle. This is not a right triangle, even though it looks like it, because every triangle I draw looks like a right triangle. But we're going to assume it's not. And we're going to start off by drawing in an altitude from C. So it's going to be at right angles to segment AB. And I'm going to label that H. Now, what we're going to do that's different than yesterday, I'm going to break up that bottom segment. And if the original full length is little c, so let's assume the original length is little c, I'm going to say one of it is x, and then the other part is going to be c minus x, because the whole thing has to be c. So we'll start off with a cosine function. If I look at angle A, I can write the cosine of A is going to be x over b. So let's write that. The cosine of A is equal to x over b. And that means I can have an expression for x, because eventually I want to get rid of x. Okay, I want to get rid of x and h when I'm all done. So if I multiply both sides by little b, I end up with an expression for x. X is b cosine of A. I'm going to box that in because I'm going to get away from it for a while, but I want to be able to find it again. X is equal to b cosine of A. All right, so the next thing I want to do is take the same side of the triangle, the x, the h, and the b, because I want an expression in terms of h. So I'm going to use the Pythagorean theorem at this point, since I'm dealing with the three sides. And I'm going to set up that relationship, which means x squared plus h squared is going to be equal to b squared. In this case, I want to solve for h squared, because I want to eventually get rid of h as well. So I can solve for h squared by subtracting away x squared. H squared is equal to b squared minus x squared. So here's what I'm going to do. I have, I'm going to box this guy in so I can find him again. And then I'm going to do the same thing with the other right triangle. I'm going to apply Pythagorean theorem to this side. So here's what that guy looks like. He is h squared. So h squared plus c minus x, quantity squared. That's going to be equal to a squared. So what I have to do is multiply this guy out and see what we come up with. H squared plus c squared minus 2xc plus x squared. That's going to be equal to a squared. All right, so let's see where we go from here. We have an h squared in here, because again, the goal is to get rid of the x's and the h's. So h squared, I have an expression for up here. I can replace the h squared with b squared minus x squared. So let me squish that in. B squared minus x squared plus c squared minus 2xc plus x squared is equal to a squared. So take a look at that thing. And here's what I have. I've got a minus x squared and a positive x squared. So they're going to go away. And I'm going to be left with an expression that I can almost deal with. So let's see what happens there. So again, here's where we are. B squared minus x squared plus c squared minus 2xc plus x squared is equal to a squared. So my x squareds are going to add to 0. And I'm getting closer to what I want. I have one more x to try to get rid of. Well, if you think back to what we did in the beginning, the original boxed in x, here's what we had. X is equal to b times the cosine of a. So I'm going to take this expression and I'm going to replace it in there, and it should start looking like the law of cosines. B squared plus c squared minus 2 BC cosine of A is equal to A squared. So this is one version. We're going to rearrange it and we're going to write it again. But this is one version of the law of cosines. So here's the meat. A squared is equal to B squared plus C squared minus 2BC cosine of A. That is the law of cosines. So let's take a look at this version of the law of cosines and just see what we can use it for. If I have A squared is equal to B squared plus C squared minus 2BC cosine of A, that means I can solve for A if I'm given two sides and the angle that's included between them. So that means this is useful for when I have side angle side, but I can also use it for side to find an angle, actually. Now, since these letters are arbitrary, I can write it in a way that might be a little bit more familiar to you. I can say C squared is equal to A squared plus B squared minus 2AB cosine of C. Let's take a look at that. So if I'm trying to find a side, the angle that goes in here is the angle that's opposite the side I'm trying to find. And then think about this. What if C were 90 degrees? So if C is a 90-degree angle, that makes little c the hypotenuse, and we have little b, we have little a. What happens to my law of cosines when C is 90 degrees? If you think of your quadrantial angles, the cosine of 90 is 0. So what would happen is this entire thing would go away and we're left with the Pythagorean theorem. So the Pythagorean theorem is just a special case of the law of cosines. That's kind of another way to think about it. Alright, so we're going to walk through one example of the law of cosines and then we'll work on more of this in class. Find side A if I have the angle A 39 degrees and the two sides that contain angle A are 12 and 14. So 39 degrees probably looks something like that. That's angle A. This is 39 degrees. So B is 12 and C is 14. This is an example of a direct application of the law of cosines. If I'm trying to find A, then A is going to be by itself. A squared is going to be by itself on the one side. B squared plus C squared minus 2BC cosine of A. So we're going to solve it algebraically first by substituting in. Well, I just kind of contradicted myself. I want to substitute in, but I'm not going to round or anything until the very end. So I know A squared is going to be 12 squared plus 14 squared minus 2 times 12 times 14 times the cosine of 39 degrees. And I know A is going to be the square root of all that. So I could process all that in my calculator and then take the square root. Or I can do it all at once. So A is going to end up being whatever I get when I take the square root of 12 squared plus 14 squared minus all this stuff. Now you have to be careful with your order of operations. If I see any mistakes, that's where I'm going to see it. You have to multiply the 2 and the 12 and the 14 by the cosine of 39 before you subtract it away from all this other stuff. And if you do it correctly, you're going to get A is approximately 8.9 if we round to a tenth. So that's an example of how we use the law of cosines. A lot of cases we'll use it in combination with the law of sines to solve various triangles and other application problems. So in class we're going to spend a couple days working these examples and doing some more challenging ones too, some that have multiple layers to it, because the formulas themselves are pretty easy. It's trying to apply them in different situations that'll be a little bit more challenging. So that's what we'll do in class.